A comet just entered our solar system, carrying a chemical fingerprint so strange, scientists are calling it a messenger from another world. This object, 3I/ATLAS, is the third confirmed interstellar visitor we've ever detected. And unlike most comets, it's glowing and releasing gas far earlier than it should, at massive distances where others stay quiet. What could create such bizarre activity? And how does it rewrite what we thought we knew about planetary formation across the galaxy? Before we move on, please take a moment to subscribe to the channel and like the video. That's the story that began on July 1st, 2025 in Chile. At the Atlas facility in Rio Hurtado, cameras built to scan the skies for hazardous asteroids noticed a faint moving speck. At first glance, it looked like thousands of others logged every night, but careful measurements flagged something strange. It wasn't tracing an ellipse at all. The arc of its track curved outward, a clear signature of a hyperbolic orbit. Even before extra data rolled in, that shape alone told astronomers the object was not born in our solar system. This wasn't a repeat visitor from our Oort cloud. It was something entirely new, later given the name 3I/ATLAS. What made the find even more compelling was its extreme speed. Calculations showed it was moving at nearly 130,000 miles per hour. To put that number in perspective, Earth orbits the Sun at just under 67,000 miles per hour. Any comet or asteroid created here is locked by the Sun's gravity. It can't just fly off at will. But 3I/ATLAS was going almost twice Earth's orbital speed, far too fast to be captured. That velocity is a direct clue to its long journey across interstellar space, where countless stellar encounters nudged it until it finally careened into our system. Only two objects had ever revealed the same kind of outsider status before: the oddly shaped body we call Oumuamua in 2017, and the active comet Borisov in 2019. Each arrival added a piece to the puzzle of planetary systems beyond our own. So when 3I/ATLAS appeared, it immediately joined a very short list, becoming the third proven fragment of distant worlds we've been able to study up close. Imagine thousands of billions of icy fragments drifting between stars, but only 3 ever caught in human telescopes so far. That scale gives you a sense of how rare these moments are. Its journey can be imagined like a stone skipping through a pond but never circling back. Instead of settling into a long orbit, it streaks past the Sun on a one-way slingshot path. By late October of 2025, it will come closest to the Sun, passing just inside Mars's orbital distance before disappearing back into the black. You can picture the curve as a long, shallow swoop that bends once and then stretches away again, marking it unmistakably as a traveler from elsewhere. But even stranger than its motion is how soon it woke up. Normally, comets stay frozen and quiet until reaching warmer regions nearer to the Sun. At distances where faint sunlight barely warms the darkness, they remain inert chunks of ice and rock. Yet 3I/ATLAS broke that pattern. Astronomers were puzzled to see a bright coma form around it millions of miles before it should have. Gas streamed outward, dragging dust with it, creating a diffuse tail. It had become visibly active while still much farther out than most homegrown comets ever do. This premature flare-up raised provocative questions. What hidden chemistry was releasing gas in such cold conditions? Was its ice made of something more volatile than water, allowing it to heat and sublimate sooner? And why would a body born under another star system carry such ingredients in the first place? The juxtaposition of its hyperbolic path and its unusual activity marked it as an outlier twice over. Not only a fleeting foreigner, but one operating under different physical rules. So on top of the thrill of watching an alien comet rush past at breakneck speed, astronomers were immediately faced with a puzzle. Its trajectory proved it didn't belong here. Its early burst of comet-like activity showed it didn't even behave like our own icy wanderers. Could the answer lie buried in its exotic chemistry, pointing to an entirely different recipe for building blocks around other suns? What if the materials that make up comets, planets, and moons in other star systems aren't the same ones we rely on here? Imagine discovering that the cosmic building blocks we thought were universal actually follow very different rules once you cross into another stellar neighborhood. That's exactly the kind of revelation astronomers found when they began examining the chemistry of 3I/ATLAS. It wasn't just a comet that behaved strangely. It turned out to be a comet built out of an alien recipe. And this recipe was unlike anything we've ever seen in comets that belong to our own solar system. When astronomers turned powerful instruments toward its coma, they found a staggering imbalance in its frozen ingredients. Most comets we've studied are made primarily of water ice, with carbon dioxide acting more as a side note than a dominant component. But 3I/ATLAS flipped that script entirely. Its gases revealed an almost 8-to-1 ratio of carbon dioxide ice compared to water. In simple terms, it carried 8 spoonfuls of CO2 for every spoonful of water. To scientists used to measuring icy wanderers around our sun, this figure was almost shocking. It didn't just stretch the outer limits of what was possible, it completely overturned the proportions we expect in a comet. Think of it like trying to follow a cooking recipe. Every traditional comet follows the standard instructions. Start with water ice as your main base, then season it with smaller fractions of carbon dioxide, carbon monoxide, and dust. You mix that up under the frigid conditions far from the sun, and you have the classic comet we all recognize. But 3I/ATLAS is like a chef who decided to throw out the main ingredient and replace it with something else. Instead of water being the bulk of the mixture, carbon dioxide dominates the dish, turning the entire recipe upside down. That dramatic change tells us it was likely formed under conditions that simply don't exist in our solar system. Why does that matter? Because the composition of a comet acts like a frozen time capsule of where it was born. In our outer solar system, temperatures and pressures favored storing huge amounts of water ice, so comets reflect that. If 3I/ATLAS contains so much more carbon dioxide, it points to a birthplace where water was scarce or less stable, and CO2 could condense more readily. That could mean it originated around a dimmer, colder star, or in a region of a protoplanetary disk where chemistry took a different course than it did here. That's why astronomers see it as a messenger. It's carrying with it not just strange ices, but the memory of a foreign planetary nursery embedded in its body. This unusual composition also helps explain why it started glowing much earlier than astronomers expected. Water ice requires more sunlight to sublimate into gas, which is why comets usually stay inactive until they draw closer to the sun's heat. Carbon dioxide, however, transitions from solid to gas in much colder conditions, because 3I/ATLAS is rich in CO2. It began to release gas while it was still very far away from the sun, where most comets would have remained frozen. Its coma didn't light up late in its journey. Activity started prematurely, and that early display is simply a chemical expression of its unusual mixture. Of course, scientists couldn't scoop a sample to check these ingredients directly. Instead, they relied on a method called spectroscopy. You can picture it as shining a prism of light through the comet's gases. Every type of molecule absorbs or emits light in a very specific pattern, leaving behind what you might think of as a barcode. By spreading the comet's light out into a spectrum and reading those barcodes, astronomers can tell exactly what elements and compounds are present. Without touching even one grain of dust, they can determine whether the glow comes from water, carbon dioxide, or something even more exotic. What they read from 3I/ATLAS was unmistakable, an overwhelming dominance of CO2 ice, unlike the standard mix we see in local comets. That fingerprint confirmed what the early activity was already hinting at. This object is built from another system's rules, carrying ratios of material we don't see in our own backyard. For scientists studying the diversity of planetary systems, that kind of evidence is gold. It tells us that the gas, dust, and ice swirling around newborn stars can combine in ways we haven't yet imagined. It also hints that rocky worlds forming around such stars could develop under very different chemical influences than Earth ever experienced. Imagine trying to measure the size of a comet when you can't even see the solid body hidden at its core. With 3 I/ATLAS, that's exactly the problem astronomers face. Its icy nucleus is completely shrouded in a glowing cloud of gas and dust, a kind of halo that tricks telescopes into showing only the blur instead of the object itself. The light we detect isn't coming from the nucleus. It's scattered by material blasted outward, like looking at a street lamp through thick fog. You can see the glow, but not the fixture, and that makes estimating its size incredibly complicated. Even the strongest space telescopes are struggling with this. Ground observations hit their limit because Earth's atmosphere smears out the view, making it impossible to isolate the tiny core inside the haze. Hubble's sharper vision finally gave astronomers a way around that, setting the upper limit on its diameter at about 3.5 miles. That means it cannot be larger than a small mountain, but at the other extreme, there is evidence suggesting it could be closer to 1,000 feet across, not much bigger than a single city block. That wide range leaves us in a frustrating position. The comet might be a staggering interstellar chunk, or it might be a fragment, only a fraction of that size. Think of the difference this way. On the larger end, the nucleus would rival the peaks of the Rocky Mountains. On the smaller end, you'd be talking about something the height of a modern skyscraper. That's roughly a 20-fold difference. And in astronomy, where measurements are usually tuned to a fraction of a percent, such a spread is extraordinary. It shows just how much the comet's activity is blocking us from answering what should be a simple question. How big is it, really? The main reason comes down to brightness. Normally, you'd measure the glow of a comet and connect that directly to how much sunlight bounces off its surface. The larger the surface, the brighter the glow. But that doesn't work here, because with 3 I/ATLAS, most of its light doesn't come from the surface of the nucleus at all. Instead, it comes from sunlight reflecting off gas and dust particles spreading outward to form the coma and tail. That's like trying to judge the size of a candle by measuring the size of the smoke cloud rising above it. The smoke doesn't tell you how thick the candle is, and in this case, the gas hides nearly every clue about the nucleus itself. This kind of issue happens with comets in our own solar system too. Their nuclei are often invisible behind their bright halos, but the difference is, we usually don't face such an extreme level of uncertainty. With 3 I/ATLAS, the estimates diverge so widely that astronomers aren't even close to agreeing. The very fact that such a gap exists makes this object stand out as unusual compared to the icy wanderers we're used to tracking. 3 I/ATLAS isn't just another comet passing through. It's a rare opportunity to study raw, untouched material from another star system, a true sample of alien worlds delivered right to our doorstep. By examining its chemistry and activity, astronomers are uncovering clues about how planets and comets take shape under different conditions than our own. If one visitor already carries such surprising chemistry, imagine how diverse the galaxy's hidden recipes must be. And with the Rubin Observatory about to begin scanning the skies, the odds of meeting more interstellar travelers soon are higher than ever.